Again, you don't have to you don't have to write down all this stuff because you have it in your sheet in front of you. The definition: f of x is, of course, it's a function. It's defined on a closed interval AB. So if we say the number j is a definite integral of f over the closed interval AB. And that j is the limit of the Riemann sums. Which is the limit as x goes to infinity of the summation of k equals 1 to n, where c is the midpoint. If. So far, so good. So if f of x is a function defined on a closed interval, and j is the definite integral of our function over the closed interval, and that j is the limit, so this equals j, this is true if the summation of our function at the midpoints times delta xk, k equals 1 to n, minus j is less than epsilon. Have we seen this before? Because this is our f of x, the limit of f of x, minus the limit L. So it's just, again, it's we learned chapter 2 stuff so we can apply these now for further things. We're getting to a point where we don't have to start doing this anymore. We're going to start defining these things using shortcuts like we did with the derivatives. So as long as this is true, then we can find the area under the curve. Once you define n, remember, once you've defined n, these all become finite terms. And as x goes to infinity, then we get a specific value. And what does this find for us? What is the limit of this? What does the Riemann sum find for us? Limit of the Riemann sum. What does that find for us? Right, it finds the area under the curve f of x on some closed interval. Okay, you have to put it through your heads. Whenever we talk about integrals, we talk about areas under a curve. When we talk about derivatives, we talk about slopes of a curve at a given point. So what this is going to equal to, now, the reason they call it the Riemann sum, that's the reason we use this symbol there, the long S, of our function dx going from A to B. Remember, f of x has to be a differentiable function. Has to be continuous on the whole thing. This symbol there is the integral sign. This is the lower bound of our closed interval. This is the upper bound of our closed interval. This is the function, and this is our index. Not our index, but our variable of integration. I might just go ahead and skip all those the derivations of it, because it'll take time. But you have to remember this f of x is actually the derivative we're looking for, because the integral finds where the derivative came from. This is actually the derivative. So we're working backwards here. So we have our theorem. Theorem 1. Integrability of continuous functions. Again, why does it matter if it's continuous? Because remember, f inside our integral, that's the derivative. In order to take a derivative, you have to be a differentiable function. It has to be continuous, and the limits have to exist at all points. That goes back to chapter 2. So if a function f is continuous over the interval AB, the closed interval, or if f has at most finitely many jump discontinuities, then the definite integral of fx dx from a to b exists, and f is integrable over the closed interval. So function f is continuous over a closed interval AB, or if f has at most finitely many jump discontinuities. then the definite integral f of x dx from a to b exists, and f is integrable over ab. So let me tell you how to read this symbol here. It's red. The integral of f of x from a to b. Since it's of x, we automatically know it's integrable with the dx function. Example 1. Example 1, f of x is a piecewise defined function. It equals 1 if x is rational and 0 if x is irrational. So what we're looking at here, we have to look at, we have two bounds of integration here. We have from 0 to 1. Let's look at, we have upper and lower. We'll be using this formula. Because we can't use the integral one because we don't know what the actual function f of x really is. So we'll use this. So for the first one, f of x equals 1. So k equals 1 to n. F of x equals 1 whenever it's rational. So these are for rationals times delta x. And it doesn't matter. It doesn't matter what we partition. Remember what a partition was? B minus a over n. That's how many how you cut the domain of your function. The partitions is how many intervals you're going to have, and then each one of them will have a delta x width. But since we have from 0 to 1, it's always going to be 1 over n. So we have summation from k equals 1 to n of delta x is 1 over n. And since this is a constant, and when we add them n times, this becomes 1 over n times n, which is 1. So for the rational functions, our summation will equal 1. For our irrationals, We use the same function. But what's our function f of x going to be for the irrationals? Our f of x equals 0 for the irrationals. So it's 0 times delta x. 0 times anything is 0. So this one's going to be 0. Let's look at the properties, some properties that we have. We know we obviously we have the sum, the difference. That's the same thing we've had earlier. So the constant multiple and the integral of a constant. We have all those the same way we just in the past. But with this, remember, integrals find areas under the curve. So here's the first one. If you reverse the bounds of integration, you've just changed the sign of the function. That's the first one. And it'll become apparent once I define how to do all this stuff. The second one is if our bounds of integration are the same, then that will give you no area under the curve. As I said earlier, when we have a constant multiple, that constant multiple can go out in front. If we have two functions and we add or subtract them, then we can expand it by doing whatever operation we have. Dx. Gx. If that's plus, it's plus. If it's minus, it's minus. So far, so good. It's the same thing we've always done, really. So when we separate them. The next one is an interesting one. Remember, the interval is a closed interval AB. We can partition that interval as many times as we want to. So we can go from A to C and then from C to B. Or this is what it's doing here. Here's A, here's B, here's our curve. And here's a value C. Instead of taking it from A to B, I can separate it into these two smaller regions and do each one of them separately. The min max, or the max min, so it's bigger, max, smaller. Inequality. If our function has a max and min on the closed interval, so that's if, then we will have the minimum of that function times the difference will be less than the integral which will be less than the max of our function, b minus a. If we have a max and a min value for our function, what are max and min values? What's the highest and lowest point? The actual value, the point of the highest point and the lowest point. We take the lowest point times the b minus a, take the highest point times b minus a, and our integral has to be between there. How do we find the max min? Because remember, we have the endpoints a and b, and we find a mid any place in the middle there, interior points for the first derivative equals 0. And the last one is called domination. If f of x is bigger than g of x on our closed interval, then the integral of f of x from a to b will be less than no, will be greater than, since f is bigger, will be greater than equal to a to b of the other function. If a is, yeah. So, and conversely, if f of x is greater than 0 on our closed interval, then the integral will also be greater than 0, will be positive. The last 7, the domination is pretty straightforward, actually. Why are those true? If f of x is bigger than g of x, why would the integrals of f of x be bigger than the integral of g of x? Let's look at these. We have two functions. There's f of x, and there's g of x. f of x is greater than g of x on some closed interval AB. So it's true. Each one of these points are higher than these points. So f of x is bigger than g of x. The integral finds what? It finds the area under the curve. So the integral of g of x is that. But the integral of f of x contains the integral of g of x. That's the integral of f of x. So it goes true. And since f is positive, it's above the x-axis, therefore its integral is going to be positive. If f of x was negative, then the area under that curve will be negative. Because we take these small intervals, the Riemann sum of these infinitely small intervals. Bless you. Example 2. Now we get to do some work. So we have negative 1 to 1 of f of x dx equals 5. 1 to 4 of f of x dx is equal to negative 2. And the integral of negative 1 to 1 of h of x dx is equal to 7. Then the integral of 4 to 1 of f of x would equal what? 2. Yeah, because since this is 1 to 4, this is equal 4 to 1, it's going to be the negative of 1 to 4. And that's the negative of negative 2, which makes it positive 2. The integral from negative 1 to 1 of 2 f of x plus 3 h of x dx. Using the properties, we can always split them up. Since that's the sum, we could break them up. 2 f of x dx plus negative 1 to 1, 3 h of x dx. Two is a constant multiple, so it can go out in front. Negative 1 f of x dx. Same with the 3, it can go out in front. Negative 1 to 1 h of x dx. H of x dx from negative 1 to 1 is equal to 5. And h of x from negative 1 to 1 is equal to 7. 2 times 5 is 10. 3 times 7 is 21. So the answer is 31. Okay, how do you do this last one? All right, with what we know from our data set up here, we can't go from -1 to 4. So we got to break it up from -1 to 1, and then from 1 to 4. Because those are what's defined up there. -1 to 1 of f5 is 5. 1 to 4 of f of x is -2. So it's 5 minus 2 is 3. Let's look at example 3. Show the value of this is less than or equal to square root of 2. Does it give us? So we're on the closed interval 0, 1. So what do we know about these two? Where are properties? Which one of these properties can we use? Since we're doing inequality, it's got to be one of the bottom two. We can't use 7 for an obvious reason. We haven't learned how to take the integrals yet. So the only thing we can use is rule 6, max min inequality. So let's look at the max min inequality, rule 6. It says the min of f times b minus a is less than or equal to the function, integral of the function, is less than equal to the max of f from b minus a. So what's the min value? Of f of x. The min value of this on this interval is what? How'd you get 0? What are you using? We only have 0 and 1 to put in there. What is the cosine of 1 or 0? So the biggest it could be is 1 plus 1 is square root of 2, so it equals there. So that's not it. So it has to be in order for that to be true, we have the square root of 1 plus 1 is equal to the square root of 2. And since that's the highest number cosine can be, this has to be the max. it really doesn't have a min because cosine of 1, we don't really know. That's radian measures. So what we have here is the integral of our function, 1 plus cosine x dx has got to be less than or equal to the max, which is the square root of 2, b minus a, which is 1 minus 0, zero, 1. So it says that 0, 1, 1 plus cosine x dx is got to be less than or equal to that. Okay, area under the graph of a non-negative function. Of a non-negative function. So the area formula is determined by this, where f is non-negative, which means that it's always going to be a positive value. And unfortunately, right now we haven't discussed the real rules, but we're getting that. We're getting very close to it. Example 4. Compute the integral of 0 to b of x dx and find the area A under the curve y equals x on the closed interval AB, or 0b, where b is a positive integer. Since we haven't discussed the integrals just yet, we're stuck to using this formula. Delta x sub k is equal to b minus a over n. Since we're going from 0 to b minus 0 over n is b over n. Now we got to figure out what C of k is. Remember, C of k is the average between the two endpoints of the interval. It's the midpoint of the interval. So it's going to start off at some interval or integer k, and then it's going to multiply by the b over n step. What does that mean? If our interval if delta x was 1, then how far is it from the midpoints? From here to here? It's also 1. Since the intervals are 1 unit wide, the distance between the midpoints is 1 unit wide. And that's why, so whatever k I pick, I go from there to the next one by adding the step size. So we get k equals 1 to n. f of cx is going to be k times b over n times delta x, which is b over n. This becomes k b squared over n squared. B is a finite number. It's a fixed number. N is a fixed number. So those are constants. Well, that brings us now to what's the summation of k? We did those yesterday. The summation of k is n times n plus 1 over 2. So we can cancel one of these n's out. So we have b squared n plus 1 over 2n. So that's, now remember we take the Riemann of it. So as n goes to infinity, the norms of all these intervals also goes to 0. So let's look what happens here. So we have b squared over 2 n plus 1 over n. N over n plus 1 over n. One over n plus 1 over n. So as n goes to infinity, this one goes to 0. So we end up with b squared over 2. With whatever b was. What was the question? It was looking for compute f of 0 to x dx, find the area under the curve y equals, okay, now we have to look at I'll look at under. So the graph of this one is a 45-degree angle. Remember, our interval is from 0 to B, wherever B is. We're looking for this area. So the area is this direct triangle is base times height. The base is from 0 to B. The height is B. Since it's a triangle, we divide by 2. So the area is B squared over 2. That's the area. So we can do it algebraically or we can do it geometrically or graphically. What that showed us, remember, that example was from 0 to B. Let's look what happens if we went from A to B. On the same interval now, we're going to go from A to B. Our function is X. We can split this up into 2 areas. The reason I did this because we know what this side is already. We know this, we just calculated it as being B squared over 2. That's because it goes from 0 to B. Well, what if we made this one go from 0 to A? If we change the direction of integration, when we went from 0 to A. Since we switch those, we have to change the sign. And we know it's going to be A squared over 2. For the same logic, this one from 0 to B became B squared over 2. As if 0 to A, it's going to be A squared over 2. But the negatives change bounds of integration. So what does that show us? We're getting closer to defining how we're going to do these integrals. So B squared's positive minus A squared. And there you have it. We do this because A is less than B for the interval. This shows us the method of how we're going to do integrations now. So it's going to be f of b, or the integral of that. Once the integral of f of x is capital F of x, we start at the very top and minus the bottom one. So this is going to be our general formula. Also, if we have a constant function, bless you. If we have a constant function, that constant goes out in front. And then it simply becomes b minus a. And since we dealt with x the last time, if we deal with x squared, we're going to get this. So yeah, each of these we will use extensively from here on out. Now, the average value of a continuous function. Now we're going to look at it with respect to integration. So the average, what defines an average? How do you find, what's the procedure? Add them up and divide by how many you have. Yeah, so since the denominator is going to be a fixed number, it's going to be constant, it's going to be the difference of our bounds. That'll tell us how wide it's going to be. Remember, it's always on a closed interval. And then once we find the integral, that'll give us the average value. So the average is also called the mean value. And it's always on a closed interval because this bounds are the lower and upper bounds of your integral. Has to be inclusive. Find the average value of f of x on -2 to 2, where f of x is equal to the square root of 4 minus x squared. We're visited by this guy again. Remember this one? Remember this function? We square both sides.
4 minus 6.
Yeah, so it's a formula, it's an equation of a circle at 0, 0, radius 2. So this is the semicircle from -2 to 2 to 2. So the area, since we're looking for the average value, is from -2 to 2. Let's look at this. It's 1/2 of a circle. Formula for circle is pi r squared. The radius is 2. So it's 4 pi over 2, which makes it 2 pi. That's gonna be the area. Let's see what else we can find. The mean value. So ours is, remember, we're at interval from -2 to 2. So we have 2 minus -2. The integral of -2 to 2. Square root of 4 minus x squared. This becomes plus, so it's 1/4. So 1/4. We just calculated this one. The area is 2 pi. We did that here. So the average value of our function over the closed interval -2 to 2. See, all we have to do, since we did this, remember, this finds the area under the curve. We did that algebraically right here. So we know this is gonna equal 2 pi. And this is A and that's B. Plug it in there. 1/4 times 2 pi. The twos cancel, so that's our average value. Because remember, we haven't discussed how to actually solve the integrals just yet. Any questions?